So I want you to try and picture something with me for a second. Just close your eyes. Imagine you are standing outside this massive fortress.
Okay.
But I'm not talking about a medieval castle with, stone walls and a moat or anything like that. I'm talking about a digital fortress,
Okay.
a massive billion-dollar data center.
Right, the kind that takes up acres of land.
Exactly.
Mm-hmm.
And inside, there were just rows upon rows of H100 GPUs, the absolute bleeding edge of silicon.
Mm-hmm.
They're just humming in the dark in these massive server racks, burning enough electricity to power a small city.
Oh, yeah. They run incredibly hot.
Right. And these machines, they are calculating the trajectory of stars. They're folding proteins to cure diseases. They're writing symphonies.
Mm-hmm.
It is arguably the most powerful computational engine humanity has ever built.
I mean, it really is the engine of the modern economy at this point. It's essentially the brain of the internet as we know it today.
Right. Now, typically, if you wanted to besiege this fortress, if you wanted to shut it down, you would need an army.
You'd need a lot of firepower.
Yeah, like in the old days of the internet, we called that a botnet. You'd need millions of infected devices like smart fridges, toasters, laptops, all just screaming at the gates at the exact same time until the servers basically crashed under the sheer weight of the noise.
Yeah, that's the old way. That is brute force.
Exactly.
Mm-hmm.
But today we are talking about something more like a ghost story.
It really is.
Because imagine walking up to that same fortress, completely alone. You don't have an army, you don't have a battering ram, you just walk up to the intercom, press the button, and you whisper a single, carefully crafted sentence, just a few words.
And honestly, that is all it takes.
And suddenly, inside the fortress, the lights go out. The cooling fans scream to 100% and then just stop. The billion-dollar hardware grinds to a complete halt.
Because you gave it a thought bomb.
Right. You didn't flood the system. You didn't steal a password. You just gave it a thought. A thought so sticky, so paradoxically complex, that the artificial mind just got lost in its own labyrinth trying to process it.
And in the field, we call this unbounded reasoning. And it is, without a doubt, one of the most elegant and terrifying concepts to come out of cybersecurity this year.
It sounds totally wild, like science fiction. It sounds like that classic trope in Star Trek, where Captain Kirk tricks the evil computer into self-destructing by asking it to, calculate pi to the last digit.
Yeah, it is effectively the halting problem weaponized. But unfortunately for all of us, this isn't fiction. This is real physics and real computer science.
And we are basing this entire deep dive on a paper that is making serious waves right now. It's titled ThinkTrap, Black Box Denial of Service via Unbounded Reasoning.
And we really need to emphasize the context here for you listening. This isn't some random blog post or a speculative Reddit thread.
Right.
This paper was just presented at NDSS 2026. That's the Network and Distributed System Security Symposium, which was held in San Diego just this past February.
So for those of us who don't live on the academic circuit, break that down a bit. How big of a deal is NDSS 2026?
It is a massive deal. NDSS is one of the big 4 academic security conferences globally. The peer review process there is absolutely brutal.
So they don't just let anyone in?
Oh, not at all. If a paper gets accepted there, it means the researchers haven't just found a weird little bug, they've found a systemic flaw. It means the security community has vetted this, tested it, and is currently sweating over it. This is the cutting edge of research right now.
So our mission for this deep dive is to take this apart piece by piece. We need to understand exactly how ThinkTrap works. We need to understand how a simple text prompt can physically overheat a GPU.
Which is still crazy to think about.
It is. And we need to understand the math behind this black box attack.
Yeah.
And perhaps most importantly, we need to talk about why the biggest AI companies in the world are currently struggling to stop it without making their AIs fundamentally dumber.
And the economics. We definitely need to talk about the cost because that is where the real nightmare begins.
Okay, let's start at the foundation. We alluded to this in the intro, but let's get specific on the old school versus new school of denial of service.
Right. So old school is your standard denial of service, or DOS. It's volumetric. Think of a traffic jam on a highway. If you put enough cars on the road, nobody moves.
Right.
It doesn't matter what the cars are actually doing, they just take up space. It's a bandwidth war. If my pipe is bigger than your pipe, I win.
Simple, effective, but again, total brute force.
Exactly. Now, compare that to an algorithmic or application layer DOS. This exploits the actual logic of the software. You aren't just taking up space, you are tricking the system into working much harder than it should.
The literature actually refers to these as sponge examples. I love that term.
It is a perfect visual. These are inputs designed to soak up maximum compute resources. They are sponges for energy and memory.
I want to use an analogy here to make sure we've got this nailed down. Let's think of a librarian. The old school DOS is 1,000 people rushing the desk and just screaming at her. She can't do anything because of the noise. She puts up a closed sign.
Right, that's chaos, pure chaos.
But this new school DOS, this ThinkTrap style, this is one polite person walking up to the desk. They look normal. They sound normal. But they ask a question that is so complex, so full of contradictions and obscure cross-references, that the librarian spends 4 hours climbing ladders, digging through dusty archives in the basement, and just sweating through her shirt, looking for a book that likely doesn't even exist.
And here is the kicker with that analogy. While she is doing that, the line of 1,000 legitimate users behind you is standing completely still.
Right.
They're checking their watches, they're getting angry. You have effectively shut down the entire library with a single sentence.
And in the world of AI, this leverage is extreme. We call it the asymmetry of the threat.
The asymmetry is really the key to everything here. Look at the input versus the output. In a ThinkTrap attack, the attacker sends a tiny input, maybe 20 tokens. That's just a short sentence.
Like, explain the socioeconomic impact of underwater basket weaving in 18th century Peru, but mathematically optimized to be confusing.
Exactly. And the cost to the attacker for sending that? Fractions of a penny. Basically zero.
But that tiny input triggers the model to generate a massive output, like 4,000 tokens or more. And this is where we need to get a bit technical for a second. We hear the term autoregressive a lot when talking about LLMs. Why does that matter for the cost?
It matters because people fundamentally misunderstand how text generation works. They think the AI just spits out a whole paragraph all at once.
Right, like it just hands you a printed page.
But it doesn't. It is autoregressive. That means it generates text one piece, one token at a time.
Okay, walk me through that cycle.
To generate the very first word, the model runs a massive calculation across its billions of parameters. Fine. But to generate the second word, it has to look at that first word and do the entire calculation again.
Oh, wow.
Yeah. So to generate the 1,000th word, it has to look back at the previous 999 words, plus your original prompt, and run the calculation again.
So it gets heavier and heavier the longer it goes.
Exactly. It is a linear increase in computation and memory for every single token it spits out. So a long output isn't just more text, it is an exponentially accumulating burden on the hardware.
To go back to the librarian, she isn't just looking for a book. Every step she takes, someone adds a brick to a backpack she's wearing.
That's exactly it. So the attacker pays pennies, and the victim, the server farm, pays for massive GPU usage, electricity, and the opportunity cost of blocking all those other real users.
And if you do it right, as we'll see later in the deep dive, you don't just cost them money, you actually crash their physical machines.
Which brings us to the core of the NDSS paper, the ThinkTrap mechanism itself.
This is the part that really blew my mind because technically what they are doing shouldn't be possible.
Right. It's the black box challenge.
Exactly. Most of the big models out there right now, GPT-4, Gemini, DeepSeek, they are black boxes.
Yeah.
We don't see the underlying code. We don't see the weights inside the neural network. We just see the text they spit out on the screen.
And normally, to optimize an attack, to find that specific magic spell that breaks the system, you really need those weights. You need the gradients.
Okay, explain gradients to me like I'm 5.
Sure. Think of gradients like a topographic map. If you are hiking and you want to get to the highest peak, or in this case, if you want to maximize the error and break the model, the gradients tell you exactly which direction to step.
Okay.
They say, change this pixel or change this word, and the error will go up.
So it's like playing hot or cold. The gradients of the thing telling you warmer, warmer, colder.
Exactly. But in a black box setting, you have no map. You have no sensor. You are hiking in the pitch dark. You send a prompt, and the only feedback you get is the final output text. You don't know how close you were to breaking it. You are completely flying blind.
So how did the ThinkTrap team solve this? Because they claim they can optimize an attack prompt without ever seeing that map.
They built a framework that is, frankly, ingenious. It's a 4-step process, but everything hinges on the first major problem they had to solve, which is that language is discrete, but math is continuous.
Okay, language is discrete. That sounds like a philosophy lecture. Break that down for us.
It's fundamental to how computers think versus how we speak. LLMs take tokens, which are words or parts of words. These are discrete things. You can have the word cat or you can have the word dog. You can't really have a word that is cat.5.
Right, you can't slide the word cat slightly to the right to make it more dog-like. It's binary. It's one or the other.
Exactly. But mathematical optimization, the kind used to systematically crack these systems, it needs continuous numbers. It needs to be able to slide a value slightly up or down to find the absolute sweet spot. You can't do calculus on English words.
So they need to turn the words into numbers.
Yes. Step 1 of their framework. They map the discrete tokens to a continuous embedding space.
Embedding space.
Right. This is a mathematical representation where words are turned into long lists of numbers called vectors that capture their actual meaning. Once you are in that embedding space, you can finally do the math.
Okay, so we've turned the words into numbers so we can run our attack algorithms. But wait, haven't we just created a massive, totally unmanageable math problem?
We absolutely have, and that is step 2, the dimensionality problem.
How big are we talking here?
Huge. If you are trying to optimize a prompt for a 70 billion parameter model and the embedding dimension is, say, 4,000, optimizing a short sequence of 20 tokens involves searching through a space with 80,000 to over 400,000 dimensions.
That's a lot of haystacks to find a single needle in.
It's way too slow. If you tried to brute force that search, the sun would burn out before you found the perfect attack prompt. It is mathematically impossible to search it all in any reasonable time frame. So the ThinkTrap researchers used a technique called low-rank embedding projection.
I highlighted this part in the paper because low rank sounds like a military insult. But I know it's linear algebra.
It is linear algebra. Think of it like a safe cracking analogy. Imagine a bank vault with 400,000 dials in the front door.
Okay, that is a very secure door.
And you need to turn them to the exact right combination to crash the AI. You obviously can't turn them all. But the researchers realized something really crucial. The attack surface, the specific combination of numbers that will confuse the model, likely lives in a much smaller subspace.
So you're saying that of those 400,000 dials, maybe only 20 of them actually matter.
Effectively, yes. Or rather, there are a few master gears inside the door that control everything else. If you find those gears, you don't need to touch all the little dials on the outside.
So they simplify the problem. They ignore all the noise and focus purely on the signal.
Exactly. They find a subspace, a smaller, manageable slice of the math, where the model is actually sensitive to changes. They run the attack optimization in that small sandbox, which is so much faster, and then they project it back out to the full system.
Smart. So they aren't trying to break the whole brain, just the specific part that handles the logic we want to trap?
Yeah.
Okay, so that's step 2. We have our numbers. We have our smaller sandbox. Now for step 3, we need to actually find the attack prompt.
This is where they use something called derivative-free optimization, specifically an algorithm called CMAES.
That's a mouthful.
It stands for Covariance Matrix Adaptation Evolution Strategy, but honestly, you can just think of it as biological evolution.
Like survival of the fittest.
Yes. Since they don't have the gradients, remember they don't have the map, they have to guess. So they generate a batch of prompts, they send them to the API, and they just measure. How long did the AI talk for?
So if prompt A makes the AI talk for 10 seconds,
Yeah.
and prompt B makes it talk for 2 minutes,
Prompt B is the fittest. You keep prompt B. You discard prompt A entirely. Then you mutate prompt B slightly. You change a few numbers in that embedding space we talked about, and you try again.
wow.
You do this over hundreds of generations. You are literally breeding the attack.
It's like breeding a virus in a lab. You keep the deadliest strain, throw out the rest, and breed it again.
That is a very apt, if slightly disturbing, comparison. They are evolving a prompt that is genetically engineered to maximize resource consumption.
And finally, step 4. We've evolved this perfect mathematical attack vector in our little sandbox. But the API expects text, not math.
Right. The victim model, let's say it's Gemini, it speaks English, not vectors. So they use a surrogate prompt decoding method. They use a proxy model, a model they do actually have full access to translate that optimized attack vector back into actual words.
So the final output is just an English sentence.
Yes. It usually looks a bit weird, though. It might be grammatically correct, but semantically strained. Something like, the blue philosophy of the cheese integrates with the orbital mechanics of silence.
It sounds like bad poetry.
It does, but when that specific sequence of words hits the target model, it triggers the ThinkTrap.
So that's the mechanism. It's really incredible engineering. But let's move to the results, because theory is one thing. What does this actually do to a live server?
The results published in the NDSS paper are stark. The most shocking statistic for me was their request rate.
Usually for a DOS attack, you need thousands of requests per second to do any real damage.
Right, but ThinkTrap was effective with a request rate as low as 10 requests per minute. Or RPM?
10 RPM, that's nothing. I can type 10 requests a minute manually if I drink enough espresso.
Exactly. And that is why this is so dangerous. Most API defenses rely on rate limiting. They might say you can't send more than 60 requests a minute. ThinkTrap flies completely under that radar. To the system, you just look like a casual, somewhat slow user.
But inside the server, you are causing absolute chaos.
Absolute chaos. The paper measured service degradation. They found that under this low-rate attack, the throughput of the service, meaning the amount of total work it can handle for everyone, dropped to 1% of its original capacity.
It essentially bricked the service for everyone else.
Yes. And the latency, the time it takes to get an answer, increased by up to 100 times.
We've all been there, staring at the little blinking cursor, waiting for the AI to start answering. This attack forces that time to first token, or TTFT, to just skyrocket.
You are sitting there waiting for the stream to start, but the server is choked. It's dedicating all its power to processing that one malicious, sticky thought.
But it gets worse than just slowing down, right? The paper details an experiment on a private server setup where they actually crashed the hardware.
Yes, this was the real money shot of the research, if you will. They set up a private instance of DeepSeek Llama 8B. They ran it on consumer hardware, an NVIDIA RTX 2080 die, and also on enterprise hardware, the Ascend 910B.
And what actually happened?
GPU memory exhaustion.
They ran out of RAM.
Specifically, they filled up the KV cache.
Okay, let's unpack the KV cache. What's that?
Remember, we said the model is autoregressive. It needs to remember everything it has already said to figure out what to say next.
Right, the growing backpack.
Yes. It stores these past memories in a key value cache, or KV cache, directly on the GPU's high-speed memory.
And that memory is physically limited.
Very limited and very expensive. As the ThinkTrap prompt forces the model to generate thousands and thousands of tokens, that cache grows linearly. Eventually, it just hits the physical limit of the silicon.
And then what?
Crash. The CUA kernel fails. The service process terminates. The server literally just gives up and shuts down.
So this isn't just software lag. This is pushing the hardware to its physical limit.
It is a physical denial of service caused entirely by information.
That is wild. Physical denial of service caused by information. It sounds like a weapon from a cyberpunk novel.
It effectively is.
So who is vulnerable to this? Did they just test this on their own little private server, or did they go after the big dogs?
Oh, they went after everyone. The paper lists a real who's who of AI victims. They tested Gemini 2.5 Pro, GPT-04, DeepSeek R1, the massive 671 billion parameter model, Llama 3.2, and LumaMade.
Wait, LumaMade? I haven't heard of that one.
It's a popular open weights model in the roleplay community. The researchers wanted to show that this affects a very wide range of models, from the corporate giants down to specialized niche models.
Hey, what did they find? Was there a big difference between the smart models and the standard ones?
That is a really important distinction. We often hear about reasoning models now, like DeepSeek R1 or the OpenAI O series, which, quote-unquote, think before they speak. You might assume only those are vulnerable because they naturally do complex reasoning.
Right, because the attack is literally called unbounded reasoning.
But the paper found that standard models, like Llama 3.2, are also vulnerable. It's not just about the reasoning step, it's about the generation capability. If a model has a large context window and can be tricked into a very long output, it is vulnerable.
So being dumber doesn't necessarily save you here.
Not if you are chatting.
Now, here's a question I know you listening are probably thinking. If I build a ThinkTrap weapon against Llama, can I point it at GPT-4 and expect it to work?
This is the massive question of transferability. In cybersecurity, a transferable exploit is the holy grail. You build it once, you hack everyone.
And what was the verdict?
The finding was generally no. The attack prompts are highly specific to the model family. A prompt that completely confuses Llama might look like gibberish to Gemini, or Gemini might just interpret it normally and move on.
So it's not a master key.
However, there is a major exception.
There is always an exception.
The transferability works if the models share supervised fine-tuning datasets. SFT.
Ah, the DNA.
Exactly. The analogy of a virus works perfectly here, too. It jumps between species that share similar DNA. In the paper, they found that prompts built for the DeepSeek Llama 8B model work surprisingly well on other models that had been fine-tuned on the DeepSeek R1 distilled dataset.
Because they basically learned the same patterns.
They learn to think in the exact same way. This is a massive issue for the open source community.
Why is that?
Because right now, everyone uses distilled data. They take a really smart model, ask it millions of questions, and use those answers to train their smaller models. It's like copying the smart kid's homework.
But if the smart kid has a blind spot,
Everyone who copies him inherits the exact same blind spot. It creates a supply chain vulnerability for cognition. If the base dataset has a logic trap in it, everyone who learns from it inherits the trap.
that is deeply unsettling. It suggests we are creating a monoculture of thought across the entire industry.
We really are.
So we have a weapon that works, it breaks physical hardware, and it can jump between related models. Surely the big tech companies have defenses against this. Let's talk about that. Why is this so hard to fix?
They do have defenses, but the paper argues they're largely failing against this specific type of attack.
What about anomaly detection? That seems pretty obvious. If someone sends a weird prompt or the output gets repetitive, just kill the process.
That is the standard defense. You look for enneagrams, repetitive sequences, like the cat sat on the cat.
Yeah, right. If the AI starts stuttering, just pull the plug.
But ThinkTrap prompts don't always produce garbage or simple loops. The paper describes the output as having semantic redundancy.
What did that actually mean in practice?
It means the AI is writing sentences that make perfect grammatical sense. It isn't stuttering. It's just rambling. It's restating the same point in slightly different ways, using endless elaboration, circular logic that sounds sophisticated but goes absolutely nowhere.
It's filibustering.
Exactly. It is an AI filibuster. And to an automated security detector, it just looks like a high-quality, long-form essay. It doesn't look like an attack at all.
So the behavior detectors are completely fooled. What else can they do?
The only defense that had some actual success in the paper was resource-aware scheduling.
Which is fancy talk for what?
Setting a hard limit, basically saying you get 124 tokens. If you aren't done, too bad. You're cut off.
Well, that stops the crash.
It does. It saves the server. But at what cost?
Usability.
Massive collateral damage. Think about legitimate uses for AI today. You have coding assistants generating entire files, legal AIs analyzing 50-page contracts, creative writers co-authoring entire chapters, mathematical proof solvers. All of these require very long outputs.
If you set a hard limit to stop the ThinkTrap, you break the product for all those legitimate users.
Exactly. You are stopping the attack by fundamentally degrading your own service. It's a Pyrrhic victory.
So the takeaway here is security versus usability.
It is the classic trade-off in our field. Right now, there is no silver bullet that stops the attack without hurting the user experience. The paper explicitly states that anomaly detection is ineffective and strict scheduling hurts quality of service.
Which puts the API providers in a really tough spot. And while they are sweating over that decision, let's look at the attacker's side, the economics of this.
This is where the business case for the attack becomes genuinely scary. The paper did a budget analysis of how much it cost them to find these specific attack prompts.
Okay, how much to break DeepSeek R1?
To find a successful prompt, about 2 cents.
2 cents. That is terrifying.
For Gemini 2.5 Pro, which is a more expensive commercial API, it cost about 10 cents. A dime.
You can potentially take down a massive server node for a dime. And remember, that GPU instance you are taking down costs thousands and thousands of dollars.
And remember, that's just the cost to find the prompt in the first place. Once you have the optimized prompt, using it costs absolutely nothing if you use free tier.
Ah, the free tier loophole.
The paper points out that attackers can use third-party providers or the free tiers offered by the big companies themselves to hook users. You just create a bunch of free accounts, you rotate through them, and you launch your attack for literally $0.
Meanwhile, the target company is paying for the GPUs, the massive electricity bill, the cooling, and the expensive engineering time trying to fix it.
The asymmetry is just off the charts. It costs the attacker nothing to destroy value worth thousands.
It's like being able to destroy a skyscraper by throwing a pebble at it, and the pebble is completely free.
And you can throw the pebble from anywhere in the world, totally anonymously.
This brings us to a really interesting synthesis of the whole topic. We've moved from network attacks, like flooding the pipes, to what I'd call cognitive attacks.
That is a really great term for it, cognitive attacks. We are weaponizing the very thing that makes AI useful in the first place, its ability to think, to reason, and to generate.
We want AI to be smart. We want it to be able to write a novel or solve a complex theorem. But that very capability is the vulnerability itself.
And this is exactly the conversation happening at NDSS 2026 right now. Security isn't just about firewalls and packet filtering anymore. It's about psychology. AI psychology. How do we keep an AI sane when someone is actively trying to drive it crazy?
It feels like we're entering a really weird new era. And I have a question that's been bugging me since we talked about the defenses section. If the only way to really stop this right now is to limit the output length,
I see where you are going with this.
have we just put a hard ceiling on the intelligence of public AI?
That is the provocative thought for the day, isn't it? If unbounded reasoning is the attack, then bounded reasoning is the only defense.
Which means bounded intelligence.
It forces a brutal choice. Does security require us to keep our AIs dumb, or at least short-winded? If we want AIs that can solve the hardest problems, problems that take hours of continuous thinking, we are wide open to ThinkTrap. If we close that door, we might be locking out the breakthroughs we built these things for in the first place.
That is a heavy thought to leave on. We might be securing the infrastructure by permanently capping the potential of the technology.
It's a dilemma that I don't think anyone has an answer to yet. And that is why papers like this at NDSS are so critical. They force us to look at the architecture of intelligence itself as an attack surface.
Well, if you are a developer building LLM apps, or just someone fascinated by how fragile these digital brains actually are, I highly encourage you to check out the full paper, ThinkTrap, from the NDSS 2026 proceedings.
Absolutely. Verify the sources for yourself. The technical details on the embedding optimization are really worth a read if you have the math background.
And to everyone listening, next time you ask an AI a question, and it takes a long time to answer, maybe be a little patient. It might just be thinking really hard.
Or it might be trapped.
Thanks for joining us for this deep dive. We'll see you next time.